Hello, dear students. I am Samir Velankar and I welcome all of you to this video on the topic Multiway Search Tree. And there are actually two types of multiway search tree that we will be learning, which are called as B tree and B plus tree. So, in this video and in the upcoming video, we will be learning about B tree, which stands for balanced. B here stands for balanced. It is a balanced multiway search tree. Balanced multiway search tree. So this B here stands for balanced. We will be learning why it is known as balanced, why the tree is balanced. But before that, let's understand what we mean by multi-way word here, multi-way search tree. It's a good idea to start our discussion with what we have learned till now about tree. Well, we have learned one type of tree called binary tree or binary search tree. We know in a binary tree, every node has some data and every node has two pointers named left and right. These are left and right pointers which point to another node, which are called left and right children. So what we have learned is every node of a binary tree has capacity to have maximum two children. Check the words. A node can have maximum two children, not more than that, because every node has only two pointers. So similarly, the node to the left of 10, the node to the left of 10 can also have two. Well, the minimum children that a node can have is 0. If the node is leaf, as you see, the node which I am marking in the diagram is a leaf node. So minimum 0 children, maximum 2 children is the rule for binary tree. We say order, here comes the new word, order of binary tree is 2. So by order what we mean, by order we mean maximum number of children that a node can contain. As in the case of binary tree, every node can point at, at the most maximum to two children. Therefore, order of the tree is 2. We may say binary tree is a two-way tree. This word can be effective, isn't it? It's a two-way tree. Why? Because if you are at any node, let's say you are at node 10, node which stores 10, then you have two ways, either left way, left method, or right way to travel the tree. Being at any node, you have got two options, isn't it? You can either take left branch or right branch. So order is 2 and we call it as two-way tree. Now, can we have something called three-way tree? Of course, we can have three-way tree such that every node will store some data and will contain three pointers. Why not? Then every node can point to three children. The child over there can also have three pointers. Every node will have three pointers, isn't it? So every node will store data and will point to three children. Then such a tree will be called as three-way tree. So we can have four-way tree, five-way tree. In general, we say that a tree is n array tree. N array tree. Keep n as 2. Just keep n as 2 for some time here. If you keep n as 2, it will be 2 array tree. 2 means binary, isn't it? 2 means binary. So if you keep n as 2, the order is 2. N here is order. If n is 2, then we get a binary tree, isn't it? You keep n as 3, we get three-way tree. It is known as three array tree. Or if you keep n as 4, then every node can have 4 children. That means every node will contain 4 pointers. So we call it as 4 array tree. There is no limit. The limit is decided by programmer because programmer is going to declare the node. While declaring the structure node, programmer can define pointers according to his or her comfort. Maybe programmer wants to create 10 array tree. Then in the structure declaration of a node, programmer can declare 10 pointers. And then we will say every node will have 10 children or can have 10 children because every node has 10 pointers. So that's in general what we call it as an array tree. Well, I repeat, till now we were keeping n as 2 because we were learning binary tree. Now we will advance to much bigger concept and we will see how to create an array tree with n larger than 2. I hope you are understanding. We want to create an array tree with n larger than 2. You will get a multi-way tree. Such trees in which every node can point to many children will be called as multi-way tree because at any node you have multiple ways. In binary tree you have just two ways, isn't it? In an array tree with n larger than 2, you will have multiple ways to travel. So hence such trees will be called as multi-way tree. So simple, isn't it? So here I have shown a diagram of a sample multi-way tree. Look, I am still not discussing what do you mean by balanced. Although the topic is B tree, let's first become comfortable with multi-way tree, multi-way search tree. So what is its appearance? How does it appear? In a multi-way tree, a node, a node can store multiple keys. Check this. Now here the mouse is hovering on a node, you can see. This is a single node of a multi-way tree. And in this node, K1, K2, K3, K4 are the keys that we are storing. By key, I mean values. Like I have stored 100, 200, 300, 400, something like that. So in this node, you observe there is a capacity to store 4 keys. We can't store more than 4 keys because programmer in the struct declaration has declared place only for 4 values. And importantly, you see this K1 key. Maybe it is 100. Let's assume it is 100. Then this K1 key has a pointer to its left. Check this. This is the left pointer. And K1 has a pointer to its right. So this, if you imagine only K1, keep the picture, keep your eye on K1 and the 2 pointers, left and right of K1. You can imagine that this is just like binary tree, where there was a node and we were keeping some key in that node and we had 2 pointers. One was left of K1 and other was right of K1. So if you imagine one unit of this node, small unit of this node, you can imagine this is like a binary tree, isn't it? But what's important is only K1 is not present in this node. Even K2 is present. There is another key K2. Then there is K3, K4. So 4 keys have been allocated or stored in a single node. It's like we have increased the capacity of the node. Previously, the capacity of the node was 1. Only 1 key can be stored in a binary tree node. We are now saying we are storing 4 keys in a multi-way tree node. Okay, additionally, what you see here is K1 has left pointer and right pointer, as you are seeing. Now K2, the other key, also has left pointer and right pointer. But observe, left pointer of K2 is nothing but right pointer of K1. Are you understanding? So this pointer on which the mouse is hovering right now, this pointer is actually shared as right pointer of K1 and left pointer of K2. Similarly, K2 has right pointer. You can see this. This is the right pointer. But that is same as left pointer of K3. K3 has right pointer. This one. This is the right pointer of K3. This one. But that's same as left pointer of K4. And K4 has a right pointer. So tell me, isn't every key having left and right pointer? Check. K1 has left, right. K2 has left, right, so on. And K4 also has left, right. Okay, so that's the organization of a single node of an array tree or multi-way tree. Now we say that there are 5 pointers protruding out of this single node. There are 5 pointers. You note there are 4 keys. I think the analysis is very easy. There are 4 keys and every key has left and right pointer. Then there are 5 pointers. If you count them, pointer number 1, this is the pointer number 1, this is pointer 2, yes, and this is pointer 3, like that. We have got 5 pointers. This is fourth pointer and this is fifth pointer. So the tally is so easy. If the node stores 4 keys or has capacity of 4 keys, then node has 5 pointers. 5 pointers. What if we stored only 3 keys like K1, K2, K3? That's the capacity of the node. That's it, we say. Every node can store only 3 keys. Then left and right pointer of K1, but same the same right pointer of K1 is shared by left pointer of K2. So K2 has left and right pointer and K3 has left and right pointer. So 3 keys are there. So how many pointers? 4 pointers. In general, if a node stores n keys, suppose there are n number of keys in the node, then number of pointers are n plus 1. Number of pointers are n plus 1. Okay, I guess you have followed it. Now, coming back to this picture, let's see what left pointer of K1 is doing. Let's see that. Now, the left pointer of K1, as you observe in the picture, I'm talking about this left pointer of K1, this one, is pointing to a node. And of course, that node should be the same structure. That node should have the same structure as its parent, because all these nodes belong to the same tree, isn't it? So the left node over here should also have capacity of storing 4 keys. Let's say K5, K6, K7, K8 is stored. Some keys, some values are stored. And of course, this node will also have 5 pointers. Definitely. Then you see this pointer. Which is this pointer exactly? This is right pointer of K1, isn't it? Right pointer of K1, but left pointer of K2 will point to a child node. This is a child node, which can also have capacity of 4 keys, as you have shown that K9 to K12 4 keys have been stored and there are 5 pointers. Similarly, the pointer, this one, which is right pointer of K2, this is right pointer of K2, but left pointer of K3 will also point to a child node and next child and next child. So how many children can the node have? 5, isn't it? Why 5? Why not 6? Because there are 5 pointers inside the node. So any node can point maximum to 5 children. If you observe the node where I am pointing right now, this node can point at most to five children, isn't it? 5 child nodes. So what is the order of the tree which I have drawn above? Now, what do you mean by order? Order is maximum child nodes. Many authors call it as subtrees also. Yeah, you can see the left of K1 over here is pointing to a subtree. This is nothing but a small tree or a tree in itself. So what is order? Max child nodes or subtrees that every node can contain or every node can point, can contain. That's order. This word is very important in the definition of n array or multiway tree. So what is the order of the above tree? Order of the above tree is 5. I repeat, order is defined as maximum number of children a node can have. So what is order of binary tree? Order of binary tree has to be 2, because every node in a binary tree can point at most to 2 children, isn't it? All right. Now further, as we have seen here, let's see the definition. I'm pointing out to this, the sentence written on the top. B tree is a balanced multiway tree. Still, I have not explained what do you mean by balanced, but I hope you have understood why it is known as multiway tree, isn't it? In which every node can store n keys. Like in this tree, every node can store 4 keys and definitely has n plus 1 pointers. So if there are 4 keys, then every node will have 5 pointers. Hence, each node can point to n plus 1 child nodes, maximum n plus 1 child nodes. Okay, so the order will be n plus 1, isn't it? So just come again. If I say, just imagine there is a node which can store 100 keys. Then what will be the order? Node is storing 100 keys. So how many pointers come out? 101. So the order of the tree will be 101 because the node can point to 101 children. I hope you are understanding. Now further, let's see distribution of the keys here. Now there are a few rules here. Now whatever keys are stored in a single node, let's check K1, K2, K3, K4. Keep an eye on the top. K1, K2, K3, K4. These keys are stored in one single node. Then all of them are always in sorted order. So you can imagine if K1 is 100, then K2 has to be something like 102. K3 has to be 110 and K4 has to be 120. Values K1, K2, K3, K4 should be sorted. Similarly, watch K5, K6, K7, K8. Value in the left child should be sorted. All these keys must be sorted. And K9 to K12 must be sorted. So the rule is values stored inside one node must be in the sorted order, isn't it? And now the second rule is whichever keys are stored to the left of K1. By the way, which keys are stored to the left of K1? Observe. Keys stored to the left of K1, K5, K6, K7, K8. Four keys are stored to the left of K1 are always less than K1. Just observe, we can put less than or equal to also, but we'll stick to less than here. Imagine that keys are never repeated. So don't imagine about equal to. So K5 to K9, sorry, K8, all these keys are always less than K1. So keys which are stored to the left of K1 are less than K1. Okay, observe these keys now. K9 to K12, check the mouse hover. K9 to K12. Now where are these stored exactly? To the right of K1. Yes, they are to the right of K1 but left of K2, isn't it? Right of K1 but left of K2. Then these keys K9 to K12 are greater than K1 because they are to the right of K1 but they are less than K2. I hope you are understanding. We still have less than greater than rule. What do you say? Which keys can be stored to the left of K2? The keys that are smaller than K2 can be stored to the left of K2. And the keys which are greater than K1 can be stored to the right of K1. So just imagine for some time, K1 is 100 and K2 is 200. Imagine. Then which keys can be stored in this node K9 to K12? You can store only those keys in this which are greater than 100 but less than 200. So you can store 110, 120, 130, 150. But you can't store 210 because it is greater than K2. All values which are less than K2 are to the left of K2. Also, all values which are greater than K1 are to the right of K1. So you can say K9 to K12, are the keys which are between K1 and K2. Isn't it? K9 to K12 are the keys which are greater than K1. And also K9 to K12 are the keys which are less than K2. I hope you understand. So which keys are stored, which type of keys are stored in this third child here, in this third child? Which keys? Yes, you must have answered it. The keys which are greater than K2 but less than K3, isn't it? And which keys are stored in this fourth child over here? This one, fourth child. Which keys? The keys which are greater than K3 but less than K4. And finally, which keys are stored in this rightmost node over here? Of course, the keys which are greater than K4 because they are to the right of K4. Are you understanding? The same rule of binary search tree is repeated here. Keys less than K1, let's put them to the left of K1, and keys greater than K1, let's put them to the right of K1. Keys less than K2, let's put them to the left of K2. Keys greater than K2, let's put them to the right of K2. Absolutely the same rule. The only thing is, single node is a house for multiple keys and multiple pointers. I guess you understood these two things. Let's scroll down and see if we are able to understand these definitions now. What do you mean by order of B tree? Order is defined as maximum number of child nodes or subtrees that a node can have. B tree shown above has order 5 because you must have seen that every node can point to 5 nodes. Every node has 5 pointers. Hence, order of that tree is 5. Okay. Note that if the order of the B tree is 5, then it means every node can store 4 keys. Yes, everyone. If the order is 5, what does it mean? It has 5 pointers. Yes, it has 5 pointers. Then there can be a key between these 2 pointers. There can be a key between these two, and so on. So obviously we have placeholders only for 4 keys: K1, K2, K3, K4. Okay. I hope you are getting used to these definitions quite gradually. All right. So in general, what if the order of the tree is n? How many keys can be stored in every node? If the order of the tree is n, then the node can store n minus 1 keys. Now let's understand distribution of the keys in the B tree. Keys stored inside a node, inside one node, are always sorted in increasing order. So K1 to K4 in the topmost node were sorted. Okay. All keys stored to the left of K1, that is K5 to K8, are less than K1. All keys stored to the right of K1 but left of K2, that is K9 to K12, are greater than K1 but less than K2, and so on. So if you imagine that there is a key like suppose K3, it will have a pointer to the left and pointer to the right. Before this, we have a key called K2. Now the keys stored in this node, whatever keys are stored in this node, are always greater than K2 but less than K3. And if we have some key like K4 here, then whatever keys are stored in this node, which I am right now drawing, are greater than K3 but less than K4. I hope you are understanding distribution of the keys. Oh, now let's understand a very interesting rule about B tree, because we are up to the topic called construction of B tree. We will be having some values, some keys, and we will try to construct. We will try to construct a B tree from scratch. And I'll tell you all the rules for constructing, just as I explained how to construct binary tree quite a few videos back. So what is rule of B tree? Let's see. The rule is every node of B tree except root node. So this rule is not applicable for root node. Okay, I repeat, root node doesn't come under this rule. So every node of B tree except root node must have at least ceiling of order by 2 subtrees. Ceiling of order by 2 subtrees. Let's see what we mean by this. Let's assume that the tree has order 5. That means 5 pointers. As order is 5, it can point to 5 children. Correct? So how many places are there to store the key here? 4 places: K1, K2, K3, K4. K1, K2, K3, K4. Now what it says is that the all nodes of B tree except root must have at least ceiling of order by 2 subtrees. By subtrees we mean children, child nodes, or the pointers which point to child, isn't it? Subtrees. We could have written child also over here. Child. Anything is possible. You can alternately use, but subtrees is a better word. Okay. So every node except root must have at least ceiling of order by 2. Now ceiling is generally shown with this symbol, ceiling of order by 2. Now what is the order of the above tree? It is 5, isn't it? 5 pointers. 5 pointers. So order is 5. So ceiling of 5 by 2. Now you check, ceiling operation means this value 5 by 2 is going to be 2.5. Okay, we are talking about actual division, not integer division. So now seal operation is going to give us the integer value which is higher than 2.5. Immediate integer which is higher than 2.5. Immediate integer that is higher than 2.5 is 3. I hope you know seal operation. Like what is seal of 3.1? As an example, It is 4 because 4 is the next highest integer I am saying above 3.1. What is seal of 4.9? Seal of 4.9 is 5. Next integer higher than 4.9 is 5. Okay. So enough of seal discussion. Now coming back to our rule, as order is 5, what does the rule state? Every node must contain at least ceiling of 5 by 2, that is ceiling of 2.5, that is 3 children. So child 1, child 2, child 3 must be valid. By valid, what I mean is, it's not necessary that there should be a node which stores something. This pointer can even be null. All these pointers can be null. But what I mean by this is that there should be some valid key stored at the place of k1 and at the place of k2. Now if you have k1 and k2 stored, only then you can say that some values can be stored to the left of k1, some values can be stored to the right of k1, some values can be stored to the right of k2. But you may not store anything in the place of k3 and k4. Let them be vacant. If you keep a key vacant, then you please try to understand you cannot have any value stored in this child. How can you have a value stored in the child over here? You cannot have a child over there because the key is not present, k3 is not present. So how can you decide which value should you store there? Similarly, you see k4 is absent over here, you have not stored k4, that place has gone wasted. Then there cannot be any child node stored. You can't make a node over here, but you can make a node to the left of k1 if you want, because k1 is valid key, k2 is valid key, isn't it? So coming back to the rule, this rule is quite difficult initially, but trust me, when you go through the construction, you will understand the rule in and out. Okay, this always happens with beginner. It happened with me too. I am sailing in the same boat as yours. But you see, what I was talking about is that if you have a node with 4 key positions, 4 keys can be stored. So there are 5 pointers. Okay. Now if I ask you, tell me which type of keys are stored in this node, in this child node. Tell me. You will say the keys which are stored in this left node are always less than the key which is stored in the first place. But what if I have not stored anything in the first place here? Then how can you have a node to its left? I am checking. I'm asking you. If you don't have a key over here, if you have kept this vacant, if you are not utilized that place, how can you have this node? Are you understanding? So to have this node, you must have some key like k1, valid key stored. I hope you are getting it. So imagine that we have k1 and we have k2. Then there can be a node to the left of k1. There can be a node to the right of k1, because now you know which keys to distribute, which are greater than k1 but less than k2. And there can be a node to the right of k2. Now, how many child nodes you have? You have child 1 here. This is child 2, child 3. And that's exactly 5 by 2, ceiling of 5 by 2, which is 3. Rule states that if you have a node of a B tree having order 5, then that node must have ability to point at least to 3 children if the order is 5. Well, the other child may not exist at all, because you have not stored any key in that positions of k3 and k4. Can you say other way? If the order is 5, then you know maximum keys are 4. You know this tally, isn't it? Then the node must store at least 2 keys. So instead of talking so much, I could have told you that the node must be at least half filled. Check my words. The node must be at least half filled. So what if the node has capacity of 4 keys? If the node has capacity of 4 keys, then you should at least store two keys in that, and let that two other keys can get wasted. It's fine. There's no problem with that. So if you have a node which has capacity of 4, then you must store at least two keys. And other two keys, you may say, no, no, I don't have any keys over there, I am not storing. This is a valid node. This is following the rule, because now you can have left of k1 some values, right of k1 some values, right of k2 some values. So you have three children over here. So ceiling of 5 by 2, that is 3. The rule is followed. Okay. Okay, I'll stop talking about this rule. If you're not followed it, it's fine. Don't worry. Just go through the definition and you will understand what I'm talking about when we actually construct the B tree. But listen, you can remember this as the node must be at least half filled. Okay? Okay. And the rule is not applicable for root. So, come again. What is the rule? Every node of B tree except root must have at least ceiling of order by 2 subtrees. So if the order is 5, then each node except root must have at least ceiling of 5 by 2, that is 3 subtrees. In other words, each node except root must store at least floor of order by 2. Now the floor is shown like this, floor of 5 by 2, and floor of 5 by 2 is floor of 2.5. Floor of 2.5 is 2 because we are looking for a value lesser than 2.5. Nearest value which is lesser than 2.5. So if the order of the tree is 5, then every node must store at least floor of order by 2, that is 2 keys. Okay, we have seen enough in this topic, and when we join in the next video, we are going to see construction of B tree of order 5, as you see in the next topic written down below there. Thank you very much.